So this is the test review for, I think it's 2.9 to 2.13. It's like the log stuff. I got like resources for it right here. This is, I think it goes, no, this is the soonest, or I think it's actually in random order, but it's stuff like these are more of the functions. These are forms, general forms, and properties. So yeah, but over here I have the actual thing, the actual review, so it's good to go over it. All right, so it's just telling us to convert the equation from exponential form to log form. This is really easy. So this is 3 squared equals 9, but it's basically 3 to the power of what is 9. 3 to the power of what is 9? That'll be 2. This one right here, same thing. Since it's 10, we don't have to actually write it because that's a it's a normal log. So we can literally just write log y equals x, because 10 to the power of y, 10 to the power of x is y. And this right here, log of r, which is our base, to the power of what equals w, and that's going to be t. And right here we have e to the power of, well, it's e, so we can just use natural log. It's going to be easier. So it's going to be ln of e, which is already inferred, power of what, which is going to be y, is equal to 3x. Yeah, because e to the power of 3x is y. Okay, this one is just to exponential, so 7 to the power of 2 is x. And it's, I guess it's already like that. And then 3 to the power of x is y. And then this one right here, there's an invisible 10, so we're just going to do 10 to the power of 2 equals y. And there's the e here, so we're going to do e to the power of 4 is c. Okay, this one right here, let me zoom out. So we're just solving. So like, this is 2 to the power of x equals 8. That means that x is 3. Right here, 5 to the power of x is 25. That's 2. 2 to the power of x equals 32. That's 5. 10 to the power of x equals 100. That's 2. 16 to the power of x equals 4. So what you're doing is you're square rooting it. So x is just 1/2. 3 to the power of x equals 1. So we know that a base that's not 0 to the power of 0 is always 1. So x is just 0. Log of 10 to the power of 10. So we're just doing 10 to the power of x equals 10. X is just 1. And right here we have 6 to the power of x is 1 over 36. Well, what you want to do is you want to flip the base, so that's going to be negative, and then it's going to be squared because 36. So it's just going to be x equals negative 2. Okay, so we did that. So this is a table. Just know how a table or a log behaves or an exponential behave. So we're just jumping by 1, 1, 1. We're dividing by 1/2. Yeah, 1/2. We're multiplying by 1/2 right here. So that's not what a log looks like. That is what an exponential function looks like. So this is just going to be exponential function. Right here, we're times 3 times 3 times 3. Right here, we're just dumping by 10, or like plus 10 each one. That is what a log behaves like, because you'd have to like multiply by a factor in order to move by like a lower degree of magnitude. That's a log. This one, you're just times 10 times 10 times 10. This one, you're doing times 2 times 2 times 2. So what you're doing here is your x values are moving by 10, so it's literally just 10x equals and your y value is removed by 2, so it's 2y. So in other terms, it's just y is equal to 10 over 2x, which is just 5x, and that is a linear behavior. So this would be neither. And then this last one, times 2, times 2, times 2, and this one's moving minus 3, minus 3, minus 3. So that is log. Okay, let's keep going. So it's asking, are these just notes? This is not an actual thing. This is just like check if you get this, because if they're inverses, if you use the composition of one another, they should always yield x, and that's pretty much it. Also the x1, y1, like if you flip them, they should be on the graph of the inverse function, and the domains and ranges are flipped. So it's just properties. Let's do these ones. So it's asking write the limit statement for the end behavior of the following functions. So lim as x, I just can't write limit functions. Hold on. I'm writing in red because it's thinner. So lim as x approaches, we don't go to negative infinity, we go to 0. So the function is, I don't know if it's f of x, we'll just call it f of x. And that's just going to be negative infinity. And as lim approaches infinity, f of x is going to go to infinity. And this one right here, same thing. Lim as x approaches 0. To specify as well in these functions, it's approaching 0 from the positive side because it can't approach from the negative side. So we just have to specify that. Or the right side, or whatever you want to call it. So f of x is going to infinity. And as lim is approaching infinity, f of x is going to negative infinity. So still the end behavior. What you can do for this is you could literally just graph it. It's going to look like this. You can look back at the general forms of a log, like over here, like the functions, where they at? Right here. So if the a value, which I think is the base, is it the base? Yeah, right here. So if the base is positive, then it's gonna look like this. If the base is negative, then it's gonna look like this. And then so if we just literally go back here, we know exactly about how it's gonna look like. It's gonna be negative, so it's gonna be like that. And then if we're gonna write the end behaviors for that, we do lim as x approaches 0 from the positive side, f of x would be infinity, and as lim approaches infinity, f of x would be negative infinity. Oh, no. Sorry. I ignore what I drew. Actually, I did it wrong. It's a positive base. I'm just an idiot. So it's going to be like this. Kind of. So it's actually going to be lim as x approaches 0 from the positive side. F of x is going to go negative infinity. And as lim approaches x, or as x approaches infinity, f of x is going to go to infinity. So yeah, just got to watch out for that. Okay, so it's asking if the function is increasing or decreasing, and if concave up and down. So to check if it's decreasing, increasing, you check the values, check concavity, you just check at what rate it's doing it. So this function right here is decreasing. I actually confused this for a while, but it's obviously decreasing. So we can say it's decreasing. And how it's decreasing, the values are beginning to turn. The values are beginning to be less negative, right? So they're being less negative. So it's decreasing at an increasing rate because apparently Precal defines a second derivative, uses it as a second derivative, and it kind of changes how you perceive it in English. So but it's at an increasing rate because it's starting to increase a little bit. Like its values are getting less negative, so it's like starting to decrease a little bit. That's why it's concave up. So it's concave. Wait. Yeah, it's concave up because the second derivative determines concavity. So right here, this function is obviously increasing, and it's doing it as a decreasing rate. You see, it's beginning to slow down. So that would be concave down. And this one right here, like we said, we know the standard form, and it's negative, so this is going to look like this. But it's decreasing, obviously, and it's beginning to, like, increase. The second derivative is going to be positive, meaning that it's concave up. Okay, so this one, we're finding the constant of k based off behavior. But we know these are log functions, so we know that the x is going to be jumping by 1 magnitude. So it's going to be like times 2 times 2. So k is just going to be 4. So times, let's see how it also, okay, so that's times 3 times 3. So 6 divided by 3, k is 2. So this is a little weird. So what you want to do is you want to kind of see how it's behaving. So it looks like what it's doing is multiplying by itself times 1 plus 1. Or it's not. Wait. Let me see how this is behaving. Times 1. Maybe it's times 2 minus 3. It is times 2 minus 3. Okay. So it's times 2 minus 3, so it's going to be 8 minus 3 is 5. Times 2 minus 3, 10 minus 3 is 7. Times 2, 14 minus 3 is 11. And then 11 times 2 is 22, minus 3 is 19. Yeah, it works. Okay. And then right here, minus 2 is going to be 1. It's going to be something. It's going to be 7. So you're multiplying by e to the 3 because that's how exponents work. You multiply by e to the 3 every time. So e to the 1 times e to the 3 is just going to be e to the 4. Oh, there's more. Let's find the domain and range of the following functions. Okay, well, it shouldn't be that hard. So you already know that this is a standard log function. So the domain of this should be just that. I don't know what in like notation wants to write this, but actually I'm gonna check this. I'm gonna see what part of notes is this. This is example 3. So I'm gonna say it's probably like this one. Is it functions yet? It is. Okay, yeah, you see, that's right. The domain is that. It just wanted us, it didn't ask for any notation. This one right here is different, x minus 3, so you always want to set it up as an equation. It's supposed to be greater than 0, or in other words, just x is greater than 3. Right here, 2x plus 3, like I said, greater than 0. You just want to subtract 3. That's just going to be x is negative 3 over 2. So this is like, you should know how to write the domain. For this one, it's obviously going to be like 0 infinity. That's a domain. Range is always going to be all real numbers. But I'm not going to write it for the other two because it doesn't really specify that. Okay, I don't know why this one's so large. So, there's like no instructions for this question. Did I just leave it out? Let me check and see where it's from, see what it's asking us to do. Let's see here. Okay, it's asking us to, just define the domain. Okay. So 3x minus 6, like I said, greater than 0. 3x is greater than 6, and x is greater than 2. So that's easy, and I'll actually write it in the form you need. So it's just going to be obviously 2 to infinity, and it's not including 2. Infinity is not a rational number, so we can't use that. This one, let's see here. I think we can factor it. Negative 24 over negative 2. That's going to be 6 and 4. Yeah, so negative 6 and 4. So it's just asking us natural log of x minus 6 times x plus 4. So it's telling us that this has two actual solutions, right? Because the normal restriction for the domain is usually just like a value or like a parameter. But here what it's telling us is that this quadratic equation looks something like kind of like this. And this would be 6, and this would be -4. Because look, it has two solutions. It has two solutions because it crosses the x-axis twice. And this will mirror the actual domain of what this equation is. And we know that it's asking us, like a normal domain of natural log, once all the values that are greater than 0, like this one right here, you see I put it greater than 0 sign because that's what makes it an actual, that's what makes it not undefined. So the only areas where these are greater than 0 are right here and right here, and not including -4 and 6. So if you were going to actually write this, it would be -infinity to -4, not including either, union, and then 6 to infinity. Because these are the values where it's greater than 0, meaning that you can actually do the natural log. Because you can't do a natural log of number 0 or negative. So, yeah. Right here. So we're just doing this okay. So it's asking, the graph of m is, okay, so this is really easy. You see that's obviously increasing, so it's not decreasing. And it's asking, is it increasing at a decreasing rate or increasing at an increasing rate? Well, as what you can see here, it's starting to become a little like negative, right? It's starting to slow down. It's starting to become like negative. The second derivative is slowly getting near negative. So I think it's increasing at a decreasing rate. Now, I was confused on this part, but yeah, no, it's B, right? Okay, so used to be confused. Okay, so which of the following pairs is the end behavior? Okay, well, I don't want to keep looking up, so I'm just gonna like plot it. It looks something like this. Okay, so as x approaches 0 from the positive side, this should be going -infinity. It works, yeah. And as it approaches infinity, it should be going -infinity. No, that's wrong. So that's not it. So as x approaches infinity, -infinity, yes. As x approaches infinity, it should be going infinity. Yep, that works. Probably B. Let's keep checking. As x approaches infinity from the positive side, if you're going in infinity, no, so we're going -infinity. And this one says the same thing, so it's wrong. So it's B. Okay, so what else do we have? We have these ones, which, okay, well, 2 tells us to do something. I don't know, I keep cutting out the instructions to problems. So, like, I don't know what it's telling me to do. But it says, is it wanting me to write it in, like, log form or exponential form? Okay. Okay, not this one. Not this one. Is it this one? Huh. Maybe it's one later in the thing. 2.12? Not 2.13. It's not even an equality. No, it's not. It's not. Is this... What does this mean? Wait, is this a different, like... Oh, it's a different... Okay. Okay, so, yeah, it's not actual notes. This part is notes, but, yeah, okay. Well, I guess I'll just, like, turn it into an exponential. So this is just saying 15 to the power of b is a. That's all I can really do. And this other one is 4 to the power of 7 is x, which I'm not going to simplify, because I'm not going to do that. And now it's asking us to do in log form. This is just 4 to the power of x is y, or log base 4 equals y when it's into the power of x. Same thing here, log base n equals 103, 1 is to the power of 4. Okay, so it says, trying to prove that they're inverses by seeing if we plug them into each other, they yield x. So this is just f to the g of x, and f of x is 3. So we're doing 3, and then we're plugging in the g of x, which is log 3 of x. Okay, boom. That cancels out, and that's just going to be x. Okay. Now we're doing the other way. Is g. Okay. G of x is log 3, and now we're going to replace that with f of x. We're going to put in 3 of x. That's going to cancel out, so we're just going to have x. Great. They're inverses. Which of the following expressions is equivalent to that? Okay, well, let me move this. Can I move this? Well, we know that in this property, what we can do to this ln x minus 4 ln y, we can move these over here back to where they were because of the property rule we have. So it's just going to be ln x to the third minus ln y to the fourth, like that. And we know the properties, if we subtract them, if we go back over here, if we subtract the logs right here, we can put them over each other like that. So let's go like here and do that. So it's just going to be ln of this value over that value, which is a, okay, I think it's the last problem. For each of the following right, condensing each expression to a single. So again, we're using that principle way up there. So this is an addition of logs with the same base, so we can multiply them. Just log 4 of xy. Okay, this one right here is subtraction of the same base, so we can just do log 3 of, and then it's 5 over z. This one right here, we're going to do it step by step. So first of all, we're going to do this part. That includes the 5. Okay. So it's just going to be log. We're not going to write 10 because we don't need to. Log 10, and then we're going to do x over 5. And then we're going to subtract log 10 of z from that. So that's a new thing. So like I said, same base, because this has a 10, same base. So we're going to do log. I'm not going to write the 10. And then we're going to, so all we're doing is we're dividing it, right? So we're doing x over 5 divided by z, I guess, which is z over 1. Or it's just the same thing as multiplying by 1 over z. So let me make that clear. So we have x over 5, and we're multiplying by 1 over z. So we just have x over 5z. 10, but I'm not going to write the 10 because that's how it's supposed to be. Okay, and there has one single logarithm to everything. Oh, yeah, that's everything. Great. So these are the resources that you'll need. I'll just go over them. This is a standard log function equation, and you see how b has to be greater than 1 or greater than 0, because if you put like log of something to 0, that's undefined. That's why the natural, like the standard form, it will never touch 0 or go behind 0, and that's also why the restrictions is default at this, because you can't go before 0. What else? Yeah, this domain, like I said, the range is going to be all your numbers, because you can go up and down as much as it wants. It just can't go, x value can't be 0 or less. So, and we have more of this, increasing, decreasing. Okay, so you see they're always increasing or always increasing or always decreasing. There's no concavity, or there's concavity, but there's no like reflection point. They'll ask you for concavity, seeing how it behaves. So it's increasing by a lot, but it's starting to decrease. So it's increasing at a decreasing rate. That's why it would be concave down. And this one right here, it's decreasing at an increasing rate because it's starting to be positive. So that would be concave up, like I said right here. Yeah, concave up, concave down. So they're always one or the other. Okay. So what else do we have? End behavior, that's easy, and you'll have to specify from this side, because you can't say like when x approaches 0, because they'll assume that you could possibly do here, like x is going here, but it can't because this is non-existent. So you have to specify with that sign. It's okay, easy. Exponential form, this, they're inverses of one another, so just remember that. Right here, general form of logs. Yeah, just this, remember b has to be greater than 0, because you can't have a base. You can't have a negative base. Yeah, you can't have a negative. Yeah, you can't have a negative base, and you can't have a base of 1, because 1 to the power of anything will just be 1. So, and also a can't be 0, because you could move a right here, and it's not gonna be fun. So, oh yeah, this change of base property is important. So, did I not have any of those change of base property questions? I could have sworn I had them. Okay, apparently not. Point is, but this is useful because, like, let's say we have already log of 4x, and we want, like, to show that it's just the same thing as k times f of x, and we know that f of x is, like, log 9. Okay, so what we can do is, like I said here, this is our original base, so if we plug that back in, we have log of 4x, it's our original things, is equal to log of the new base, which is 9x, over log of 9, 4. Now, let's move this over here. Now we have log 9 of x over log 9 of 4, which is the same thing as saying 1 over log 9 of 4 times log 9 of x. And what we have here is it's asking us to do like f of x times k, and it tells us that f of x needs to be log 9 of x, and we have log 9 of x, so this will be f of x that was determined what am I writing with? I'll just do it in highlighter. This will be f of x, which is what we determined before, like it wants us to be f of x, and this will be k, what it's multiplying to. So that's k, that's f of x. That's how you use this as well. And yeah, they're all dilations of each other. So like the basic graph is going to look like this. Another graph that's another log will look like this. And you'll see that they're literally just vertical dilations of one another. Power properties, should know this. This one, these are both important, also important. And what it's just saying is that you can drag this here, or you can drag this here. Either way. Yeah, right here. So example, this, like it. Nope. This, drag this here, 7. So we have 7 log 3 of y. Great. That should be everything. Yeah, that's everything. All right, doodles.